Hi everyone, welcome to my IGCSE Chemistry course. This is the first lecture of the entire series. So before I begin the lecture proper, I would want to go through the structure of my lectures so you can anticipate and know what to expect in the coming slides. First and foremost, obviously, we'll go through the title card about the topic that we will be learning today. Subsequently, it will be followed by key objectives or learning objectives. These are things that you should look out for in the lecture itself. Then we will go through the lecture proper with the lecture materials. Periodically, we will go through something called active recall questions. These are questions to help you better understand and grasp the important points of the lecture itself. Last but not least, we will go through the summary, basically a reflection of the learning objectives, and hopefully by then you can or you already have a proper grasp on the important concepts. If not, do not fret, you can always rewatch the lecture itself. So without further ado, let's start with the first lecture itself. This is the lecture on states of matter. It is one that is relatively simple, but it is an important one to start with when it comes to chemistry. As mentioned earlier, here are the lecture subtopics. So we will go through solids, liquids, and gases and what they are. We will go through kinetic particle theory. The most important part of this lecture is the changes of state, and we will go through some important points on effects of temperature and pressure on gas as well as diffusion before rounding out the lecture with the summary slide. So here are the learning objectives. I will not read it off the screen. You can take this time to pause, read through, and see if you can spot these important points throughout the lecture later. One example would be explain how matter behaves. That is actually the crux of the lecture here today. So let's go through from the very beginning and what are solids, liquids, and gases. One thing you have to understand for this and subsequent lectures is that everything in the world is made up of some form of matter. They are basically made up of tiny particles. But these tiny particles eventually, or actually everything in the world exists in three types or three states of matter. At least that is what you need to know for now. And the three states that I am talking about are solids, liquids, and gases. One prime example that you can see from everyday life is water. And water exists in solid, liquid, and gaseous form, as you can see in the picture itself. As solid, water exists as an ice cube, and water, as you commonly know it as running tap water, it exists as liquid most of the time. Last but not least, water can exist in gaseous form, in the form of water vapor or steam. So the key to understanding states and how they behave is to understand particle arrangement. As you can see, the particles, tiny particles that I mentioned earlier, are arranged very differently across the three states. In solid, liquids, and gases, you can see some form of differentiation, or they differ from one another. And that can be further explained by this table you see here. I can safely say this table is one of the more important points of this entire lecture. So when you have the time, pause and try to remember and understand each and every point that is listed in this table. Okay? Without further ado, I want to go through each row itself so that you can have a better understanding of what is listed here. Okay, so for particles in a solid, its arrangement is close together. It's what you see in the picture on the right hand side. Particles in a liquid, you might not be able to see it here, but actually it is slightly spaced apart when compared to solid particles. particles in a gaseous form, you can see that they are actually far apart. You can see ample space between each and every particle. Next, we'll go through formation. As you can see, solid has a regular formation. It's uniform throughout, whereas liquid is irregular. As you can see, it is actually taking up the entire bottom of the container. Whereas gaseous or gas form, particles in a gas form, you can see that they do not have a proper, quote-unquote, proper formation. They exist in a random formation. One thing that you might not be able to see in the picture here, but it is a very important key point nonetheless, is the forces between the particles. I want you to remember that particles in a solid has strong forces between the particles itself, whereas particles in liquids, they actually have less stronger forces between each particles when compared to solid. And last but not least, for gaseous form, there are weak forces between the random moving particles. Talking about movement, let's move on to the next row. Again, you might not be able to see it here, but what you need to know for now is that particles in a solid will vibrate in its place. Basically, it will just vibrate in its uniform formation. Whereas liquids, the particles in liquids rather, tend to slip and slide over one another. One prime example from everyday life is, let's say if you were to fill up water in a balloon, you can see that the balloon itself does not have a uniform shape but actually the balloon itself will tend to flip and flop in its current state. Okay? Particles in a gas form tend to move freely in its random formation. Okay? And last but not least, one important point is what happens when you apply pressure to the particles in three different states. When you apply pressure in a solid, the volume does not change. You can take one prime example from everyday life, is if you were to put pressure on an ice cube, the ice cube just stays as is. There's no formation change or pressure change or volume change rather in that ice cube. And when it comes to liquids, the same can be said that the volume does not change when you apply pressure, but the volume does change in gases because particles can move about closer to one another, resulting in volume change. And why is that so? The main reason why is because the particles in gaseous form has a lot of space in between the particles. So when you apply pressure, what you are basically doing is just pushing the particles together. We will actually go through this key point later in the lecture itself. So pause right now. I want you to pause and try to absorb as much as you possibly can from this table before we move on to the next slide. Excellent. Now we have come to the active recall question for this segment. The active recall question for this is to draw the particle arrangement for all states of matter. If you recall, once you draw and understand how the particles are arranged in three states of matter, you can better remember and understand how they behave as well. So this active recall question is actually very important. Next, let's move on to the kinetic particle theory. Now, this might sound very complex, but it actually helps explain how matter behaves. And there's only three key points that you need to know. Matter is made up of very tiny moving particles, such as atoms, molecules, and ions of different sizes. Do not be afraid of these terms such as atoms, molecules, and ions. You will go through them in the second lecture itself. Just know for now that everything in the world is made up of tiny moving particles. Okay, so the second part of the kinetic particle theory is to know that particles are in constant motion. This is one mistake that I think a lot of students make, especially early on, thinking that particles in a solid, for example, does not move. If you remember a few slides earlier, we saw that particles in a solid does move and it does vibrate in place. Okay, the same can be said obviously in liquids and gases as well. And one thing to remember is that the higher the temperature, the faster the movement. Again, do not be afraid. This is something that we will go through again in further detail down this lecture, down the road in this lecture. And last but not least, for the kinetic particle theory is that heavy particles move slower than lighter particles. This can be said with, or this can be gleaned from everyday example as well. Let's say, for example, a truck moving down the road will definitely move a lot slower compared to, let's say, a motorbike on the road. Okay? I know that it's a lot to digest for kinetic particle theory, so take your time, read through, and remember these three main points. Okay? And you might be wondering, how do we understand so much about tiny particles when you cannot see them with your naked eye? The main reason why is because chemistry and science in general has come up with so many different techniques to observe these particles. And these techniques are called modern imaging techniques such as X-ray, crystallography, microscopes. And down the road, I believe there will be more and more techniques, thankfully, so that we can better understand particles in general, not just in chemistry. So we come to the active recall question 2. What are the three main points of kinetic particle theory? Okay, we've come to the bread and butter of this lecture, the changes of state. How does, let's say, ice turn into water vapor? Okay, one thing you need to know is that changing states require a change in energy states, as you can see in the diagram on the right hand side. This change of states can come in the form of either increase or decrease in energy. And you will come across different forms of energy down the road, especially in chemistry and physics. But one thing that you need to understand now is heat and kinetic energy. Heat, like the name suggests, heat energy comes about when you heat something up, when there is a source of heat, for example, on an open flame. Kinetic energy, basically in simple terms, is just moving energy. Basically, kinetic energy causes something to move about. Okay, in simple explanation, at least for now. One thing that you will see commonly in changes of states is that the differentiation or the interaction between the energy of the system and the forces of attraction. Again, forces of attraction is something that we learned earlier, if you remember, that, for example, particles in a solid have strong forces of attraction, whereas particles in a gaseous form usually has weak interactions between the particles. Okay, you might not understand what is energy of the system. So in simple terms, energy of the system refers to the thing itself. Let's say if you are talking about ice melting, the energy of the system refers to the ice itself. Again, do not fret, we will explain this in actually the next few slides. Okay, so let's talk about how you go from solids to liquids. This is a simple one. Okay, we'll start off simple. When a solid is heated, as you can see, the particles will vibrate faster and faster as they gain energy. If you remember, particles are already vibrating in place when it comes to its solid form. But when you heat it up, what happens is that heat energy will be converted to kinetic energy. Basically, remember, kinetic energy causes something to move. The particles were already vibrating in place. Now that there is an increase in kinetic energy, the particles will move even faster and faster and faster. What happens is that the particles tend to push against one another and expansion occurs. When the expansion occurs and you keep heating the system, again, system refers to the ice here, what happens is that the heat energy weakens the forces between the particles and overcomes the forces of attraction, causing the bonds to break apart, the forces of attraction between the particles to break. And once that happens, the particles is able to slip and slide over one another. Now, the keen observers might be able to see or might be able to observe that slip and slide over one another is something that particles do when they are in the liquid state. Excellent. So particles, when they go from solids to liquids, again, they are heated up, they vibrate faster and faster, and then what happens is that the forces between attraction between the particles break, and then they are able to slip and slide over one another, as you can see in the picture down below. The point of which the particles go from solid to liquid is called the melting point. Okay? So the same thing can be said when you go from liquids to gases. How do you go from, let's say, water to water vapor? One prime example from everyday life is, let's say, if you were to heat up water, if you were to boil water, what you notice is that you see steam coming out from your kettle. And a similar process occurs. You heat the system now being water itself. What happens is that the particles vibrate faster and faster, weaken the forces of attraction, and boom. What happens is that the particles are now far apart with weak forces of attraction between one another. Again, those of you who are keen observers can notice that that is what particles do when they are in gaseous form. Excellent. So obviously when liquids turn to gas, they don't go through something called melting point. They go through something called boiling point. Excellent. So that is something that you can glean from everyday life. You boil water, that's why it's called boiling point. Okay. One key thing I want to go through here in this slide is, you can see the second line, that is heat energy. So you introduce heat energy in the form of fire in this case. What happens is that you introduce heat energy, that heat energy is converted, or rather increases the kinetic energy found in the system. Okay, again, increase the kinetic energy, obviously particles will tend to move faster and faster, overcoming the forces of attraction. I want to pause here a while and go back a few slides to maybe point out an important point to help explain the previous two slides. Okay, so as you can see, for the last two slides we were actually talking about the last sentence you see on this particular slide, and that is the energy of the system versus the forces of attraction. Again, you heat up the system, the kinetic energy of the system increases, that causes the weakening of the forces of attraction, causing the eventual change of states as well. Last but not least, another point that is important when it comes to change of states is, how do we go from, let's say, gas to liquid? So now we are going in the reverse. You do the reverse of boiling. So what is the reverse of boiling? It's basically just cooling. You're basically now taking away heat energy from the system. When you take away heat energy from the system, the particles tend to slow down. When particles slow down, what happens? The forces of attraction between the particles get stronger and stronger. Basically, that is explaining the, I think, fourth line you see in bold there. Forces of attraction becomes more significant. It's basically just a complicated way to say that the forces of attraction increases, causing the particles to move closer and closer together. So let's say gases, the particles move closer and closer to one another, and boom, now they are slip and sliding over one another. What do you call that? What state do you call that? That is basically your liquid state. and you can safely say that the gas has condensed into a liquid. So one key important point I want to talk about now is the heating curve. Basically, for every process you see here, be it, let's say, melting or evaporating or condensing or even freezing, something that we haven't talked about, yet you can see that liquid freezes to form solid. Obviously, you can take water and you freeze it. So all four of these processes has something called heating or cooling curves. As you can see, the most important part of these curves is actually the stagnant points, the straight lines, horizontal lines you see in the diagram. You see that horizontal line from B to C and D to E. The key thing here is you need to remember for all these curves is that the temperature will remain constant until the last bit of the system converts to the next state. So let's take one example. Okay, as you can see from B to C, ice is actually melting from solid to liquid. So the moment the last bit of the ice has melted, boom, now the temperature will slowly rise from C to D. As long as there is some bit of ice left, the temperature will actually remain constant. The same can be said about the vaporizing of water, basically changing from liquids to gases. The temperature will stay constant until the last drop of water evaporates and form gases. Then and only then you can see that the temperature will rise from E to F. Okay? Again, the same can be said for cooling curves. So cooling curves is basically just the opposite. Again, the temperature will remain constant between B and C and E to F as well. Okay? So basically what they are saying is, for example, freezing liquid water, the moment it reaches F is when every last bit of liquid in the system has frozen. And now it starts to cool down even further. Okay? Okay, so one key thing about boiling and melting points is that the stronger the bonds are between the tiny particles, the higher the melting and boiling points. It makes sense. If the forces itself is very strong between the particles, you will need more and more heat energy and more heat energy to convert it to kinetic energy, so that the particles can move faster and faster to break and overcome the forces of attraction. Okay, as you can see that this diagram, or this table rather, is rather daunting. Do not be afraid. There's no need for you to memorize this table. It's basically just to showcase or to show that the stronger the particles are between each other, the higher the melting and boiling points. Okay. Actually, we can just take one example you see here. Let's say we take lithium versus, let's say, water. So you can probably guess the bonds in lithium is a lot stronger, let's say, in water, because water, it melts at 0 degrees and it boils at 100 degrees. Whereas if you were to compare this to lithium, as you can see here, the melting and boiling points are 180 and 1342 respectively. Okay, one key thing that you have to remember is that melting and boiling points will help you in the chemistry lab when you are carrying out your experiments to see whether something is pure. What do I mean by pure? So let's say water, for example, coming out from your tap versus seawater. Seawater is not pure because, as you know, sea might be contaminated with debris or might be contaminated with sand and obviously contaminated with salt itself. Whereas, let's say, compared to water coming out of your tap, let's say distilled water, it is definitely a lot purer compared to seawater. Okay, we will talk about that in, I think, lecture 2, so do not worry about that too much. Excellent. So let's take a breather. Let's go through the active recall question for this segment, which is to draw and explain what happens in the heating curve of water. If you can remember, there's only one key important point that you have to include in your curve, whether it be heating or cooling curve. I want you to try to recall. If not, you can refer to your notes and see if you can remember that. Okay. When you are drawing your heating or cooling curves, it would help if you can talk through the entire process. See if you understand the crux of this lecture. Okay? Okay, so let's move on to something a lot more simpler and more relaxing, I feel, at least. The effects of temperature and pressure on the volume of gas. Why are we studying only gas, you might ask? If you can recall in the table, the first table of this entire lecture, the pressure, when you apply to solids and liquids, the volume does not change. But if you were to apply pressure and temperature to gas, there might be some change. And the main reason why is because if you remember, there is ample space between the particles when it comes to gaseous or things in gaseous form. So as you can see in the picture here, when you heat up the balloon, it tends to be bigger. When you cool down the balloon, it tends to become smaller. Why is that so? I will give you 30 seconds to try to guess why this is so. One key example is to try to think of, again, heat energy and energy of the system versus forces of attraction. Apply the same logic that you've learned earlier in heating and cooling curves as well. Ready? Okay, if you're ready, let's move on to the answer itself. So the pressure itself is caused by the gas particles moving around in the balloon. It's moving in random formation, hitting the balloon all over the place. So basically the balloon itself, the container is elastic in nature. Basically what it is saying is that you would not be able to see this change if the container itself is solid. Let's say a Tupperware, then you will not see this change with your naked eye. But because the balloon itself is elastic by nature, you can see the change in temperature and pressure on the volume of gas because of the elasticity of the balloon itself. You heat the particles tend to heat one another because of the increase in kinetic energy, thus causing the balloon to get bigger and bigger. Try to pause and grasp this explanation. Again, try to think of it this way. You are heating the system being particles in the balloon. The particles tend to move a lot faster than ever. They hit one another faster and faster. What happens then is that the balloon gets bigger and bigger and bigger. Whereas, let's say if you were to cool the system, basically what happens is that the particles tend to slow down. When the particles tend to slow down, what happens is that the balloon deflates. The balloon no longer is hitting the side of the particles actually rather are slowing down. Once they slow down, they do not hit the sides of the container as much as, let's say, when compared to the particles when they are heated inside the balloon. So in summary, what I'm trying to say here is that the temperature increases, the volume will increase as well. Again, so temperature decrease, the volume will decrease as well. Excellent. Okay, so what happens when you increase pressure instead? What happens when you mess around with the pressure instead? So when you increase pressure on gases or gas particles rather, one example would be increasing the amount of gas in the bicycle tire. What happens is that the particles are pushed together closer and closer to one another. Now they are basically they are being pushed closer and closer to one another and they are hitting against one another a lot more. as you can see the second line here, resulting in more frequent collisions between particles. More collision eventually results in more energy, heat energy rather, being produced because of the frictional forces at play. You can actually test this for yourself. If you were to pump the bicycle tire, you can actually feel that the tire itself is actually heating up. Why? Because you are increasing pressure. Again, you increase pressure, the particles are pushed closer and closer to one another, they're hitting against one another a lot more, thus causing more energy, more heat energy rather, to be produced. Yeah, so basically this is just what I've explained earlier. So again, as you can see, bicycle pump gets noticeably hotter and hotter in temperature. Excellent. So now we have come to the active recall question for this segment is explain what happens when you heat or cool a balloon. Basically, I've just gone through that. Pause this lecture and see if you can recall what I have just mentioned. Okay, we'll go through the last key concept for this lecture before we call it a day. This is going through diffusion. Basically, what is diffusion? It is basically defined as the intermingling of substances by natural movement of particles. That's just too complex. Basically, what it's saying is that particles move from one place to another. Okay, one prime example would be smells at a restaurant. You cook something in the kitchen, you yourself as the customer can smell it when you're seated in your seat. Main reason why is because the gas particles, the smells, is diffusing throughout the restaurant. Okay, but obviously in examination you need to remember the definition that is actually listed on the screen right now. But in everyday conversation you can just remember diffusion is basically particles moving from one place to another, especially when it comes to smells or gaseous particles. Okay, diffusion is actually centered around something called Brownian motion, which is discovered by Robert Brown in 1827. Do you need to memorize that? Definitely not. This is just a key trivia for this lecture. So he observed that pollen grains move around random motion in water. Okay, so basically it's the same thing as, let's say, smells or dust particles moving around in your room. Maybe one day if you come across a dusty space, you can see the dust particles in the light moving around randomly. Basically what you are seeing is diffusion is taking place. Brownian motion basically describes this as the random motion of particles. So diffusion is actually explained by kinetic particle theory because, again, particles are always in motion. If you remember that second point, I think, in kinetic particle theory. Okay, so definition number 2 is that diffusion is described as a random process where particles mix and spread through collisions with one another. I think in examination, in my personal humble opinion, you should remember this definition instead. It is something that you can actually remember off the top of your head as compared to the first definition. Okay, so try to remember, or I don't like to use the word memorize, try to understand and remember this definition instead. Okay, so obviously diffusion occurs faster in gases than in liquids. One prime example, the one I used earlier, is smells in a restaurant. Once you cook something in the kitchen, you can definitely smell it when you are seated in your seat. Okay, diffusion again increases when the process increases or is faster when you increase the temperature. Again, same thing that we talked about in changes of state. If we talk about energy of the system, you increase temperature, increase the heat energy, increase the kinetic energy, and eventually overcome the forces of attraction and etc., causes the increase in diffusion process as well. So here are real life examples of diffusion in everyday examples. Hydro dipping, I don't think it is cool right now. I think it was quite cool in COVID times, hydro dipping. And one example is cooking. So as you can see in the first picture you see here. So rate of diffusion obviously is different for different particles. If you remember something about the kinetic particle theory, is that the third point is that heavy particles tend to move a lot slower compared to lighter particles. Okay, so as you can see, the gray part there, it doesn't form in the center of these two things, hydrochloric acid and ammonia. Why is that so? Which one do you think moves faster and why? Can you pause this video and try to guess? Okay, so one example is, actually the main reason why that gray compound, they call it compound, does not form in the center of the tube is because ammonia is a lot lighter. Ammonia is a lot lighter and travels a lot faster compared to the fumes of the hydrochloric acid. So ammonia moves faster, so it covers a lot more distance as compared to the fumes of the hydrochloric acid, and it meets closer towards the green bubble you see there. Okay, we will go through more on this, I think, in your practicals in school and definitely down the road in future lectures as well. So excellent. This is the active recall question. Try to remember the answer off the top of your head. See if you can remember the answer as to why this occurs. Okay? Excellent. We have come to the summary of the lecture. This is basically just a reflection of the key or learning objectives you saw in the first slide also of this lecture. Pause and see if you can explain all of this in great detail. If you can, excellent. It means you have understood this lecture in great detail and you are more than prepared to move on to the second lecture of the series. I wish you all the best, and if there is a need to, take your time and rewatch this lecture. Everybody learns at different speeds. Be kind to yourself, and I shall see you in the next lecture, I believe. Yes, I shall see you in the next lecture.